Hi, everyone. I'm Negin Raoof. I'm a PhD student at UC Berkeley, advised by Alex Dimakis, and I'm here to present OpenThoughts, our project aiming at curating best open source reasoning datasets. So we all know about reasoning and the advancements in reasoning benchmarks over the past year, like almost it's many years since the release of OpenAI's O1 model. And I always want to go back to this graph when we talk about that to see, like, over the past year, we can see how, like, the huge advancements in reasoning benchmarks like AMY, which is like competitive math questions, or SUIBench, which we talked about a lot today. And it's very interesting to know how such tasks can benefit from long chain of thought and test time scaling. Kind of like we see this like huge improvements over the these benchmarks. One thing that was a very like a huge turning moment during the past year was the release of DeepSeek R1. And it was very beneficial because now we had the weights of these models open at our hands. Another interesting thing is that we had some information about the details of the training pipeline of this model. And this was very useful for the open source community and the research community. Another interesting thing about, like, as we read about the details of the training is that DeepSeek R1 is actually an SFT model. It means that it's been basically trained on, this is the model itself has like 600, almost like 700 billion parameters, but it's been trained on a combination of 600K reasoning and 200K general QA samples. These samples were generated by a model that was developed with RL, but the model itself was just like trained using SFT. And this was very surprising to us. Along with the big model, they also released these smaller distilled models in the scale of 1.5 to 7B to 32 to 70 billion parameters. This was, again, very exciting for us because this is like the scale at which is feasible for us in the research community to actually try to reproduce these results. So I think it's very valuable to start looking into how you can actually get performance comparable to these models because, first of all, you can have control over the data. Like you can have transparency. You can mitigate a lot of privacy issues once you start building such open source data sets. You can like basically start like tuning your model for a specific performance in a specific benchmark, and then you can also like have all the costs controlled. So a little bit of so these are basically the questions that came up to our minds. Okay, if we want to start developing such a model, what type of data we need, how much data we need, and like if we want to actually give you a recipe, not just a data set, but a recipe to come up with such models, what are the best choices at different stages of data curation? A little bit into the history from what we know, I think SkyT1 was the first project that did this from the Skylab at Berkeley. And they started with 17K questions sourced from, high quality questions sourced from the internet. They started annotating these questions using QWQ model. And surprisingly, they were able, like their 32B model was able to achieve O1 preview level results. So within the datacomp community, we are always very interested in solving the question of, given a fixed model and a fixed training recipe, how can you iterate over your data set to find the samples within the data set that like perform the best? And so the natural question for us was to start looking to reproduce these models. I'm gonna like kind of like go fast forward through these slides because these slides kind of go over our very first attempt in how, like, basically finding the available sources on the internet, evaluating these sources on downstream benchmarks, kind of finding, okay, which sources are more valuable to us, and kind of scaling the same recipe that that SkyT1 had, and testing whether verification matters or not. But there is no science to this point. Surprisingly, even like our initial efforts kind of got us to a performance matching the Distill R1 models. But again, like we haven't done any science. Like this is basically projects that we did over like weekends or like 48-hour projects that we did, and we were already like seeing very good signals. But the goal here for us is to actually come up with this recipe. And we need to, like going back to the questions that came up to our mind, we started like designing this pipeline. So the first part of the pipeline is sourcing high quality questions from the internet. Then we look into, okay, what are the best strategies for mixing these questions? Then we ablate and look into different filtering mechanisms for questions. Once we have a high quality set of questions, we use a powerful model, bigger model to answer these questions. And once we have the question answers, we look into what are the different best strategies for filtering the questions given the answers. And at the end of the day, once we have a good set of high quality question and answers, we look into, okay, now what is the best teacher model that we can use? So we have ablated all these like steps of this pipeline through almost 1,000 experiments, and we have over, I think, like 5,000 data sets and around 3,000 models that are all available on Hugging Face online, all the models that we trained over this project. And so at the end of the day, this is basically the scalable recipe. And in these graphs here, you can see the performance of our recipe across 3 different domains. So all of our experimentations were done across 3 different domains: math, coding, and science. And on the x-axis here, you can see the scale, the data set size. And it's important to note that basically just expanding the size of the data set can get like exponentially more expensive as we go. So it is very interesting to see that, as you can see, our OpenThoughts 3, our final data set recipe, kind of maintains this like advantage that it has over across different scales. And our experimentation, actually, so yeah, these are the final results. So by the time that OpenThoughts was released, this was the state-of-the-art open data reasoning data recipe for SFT, and then you can see the performance of our model on the benchmarks that we used during our development phase, as well as the held-out benchmarks. So now I want to actually go into the interesting part of the talk, which is basically the interesting findings that we had. And I just want to go over this like setup initially to basically just set the ground. So throughout all the ablation experiments that we did, we had a fixed set of 31K samples, basically. And all the annotations were done using DeepSeek R1 unless stated otherwise. Throughout each scale, all the hyperparameters were fixed, and we used the Qwen 2.5 7B instruct model across. So how we evaluate the performance of a data set is we take this base model, we train it on the data set, and then we measure the performance on a downstream benchmark. So very first cool finding of the paper is that we realized that actually the quality of the source questions matter a lot. And it's important to note that like all of these questions are again like fed to DeepSeek R1. Basically the answers are generated from the same model. But where you get the source of the questions can actually play a huge like difference in the downstream performance of your trained model. And what's also very interesting is that combining this like data from different sources doesn't always help. So we realize that like across the math domain, if you actually take the top performing data set and don't include the data sets, the data sets that are like scoring lower, doesn't help you. For science and code domains, we realize that combining the top 2 performing domains, it performs the best. So now that we have our set of questions, then we look into, okay, what is the best strategy to filter the questions? And we see that it's actually very important to filter the questions. This strategy is actually very interesting. So you just take a cheaper, smaller model like GPT 4.1 mini, and then you answer each question using this model, and you just like look into the length of the answer. This already gives you a very good statistic for filtering your questions in math. For code, it's a bit different because like coding questions can have answers of different lengths. But if you just use a cheaper model and ask the model to rate the difficulty level of your questions, this already gives you a very good signal about how you can filter your questions for these tasks. Another very surprising finding is that we realized that the diversity of answers are very important. And this means that basically you can have, note that all of these experiments are compute controlled. So the overall size of the data set is fixed. This means that if you have around 31K questions and you take only 2K unique questions, but then you sample these 16 times, you actually get a very good score. This is it's very actually useful if you think about it, because this means that it's a very straightforward way for scaling your data set and seeing actually a boost in the downstream performance easily. This showed us that this strategy actually gives you a better performance than just keeping your questions that are very close to each other and just answering them just once or even 4 times. But also note that we never went over 16 times, but it could be totally possible that even annotating each question more than 16 times can also help. Very interesting finding, contrary to, I think, the common belief in the community. Filtering based on the answers didn't really give us a good signal. If you think about it, first of all, the average performance here from the lowest strategy to the highest strategy is not the gap here is not very large. And everything, basically a lot of these could be also within the noise. But it's interesting, if you just randomly sample, or if you ask an LLM to verify the final answer and then filter out the incorrect the samples with incorrect answers, we saw that random sampling kind of also does very good, and we didn't see a strong signal that verification actually helps. Filtering for verification actually helps. So this is also very surprising to us. We tried annotating our questions with multiple different teacher models. And it's interesting to note that we saw that if a model actually does better in these benchmarks, it doesn't necessarily mean that the model is a better teacher model. Across these 3 models, Qwen is I think the worst performing model itself on the benchmarks, but it is the best teacher model. It is again important to note that the base model that we are training here is from the same family, but still we don't have a very scientific justification for why Qwen here. One thing to note is that we realize that Qwen is the most verbose model across these models, but we don't have a very solid justification of why it's actually the best teacher model. We also tried, I think, Claude models, also performed very poor. In these plots, you can see how our data, different stages of our pipeline kind of stack up, and this shows us that these advantages that we see kind of are maintained across the scale. And so the data set that this is the final Sankey diagram of our pipeline. And the data set that we kind of tested at 30K size was we were able to kind of scale it up to 1 million data points. This data set was trending a #1 data set on Hugging Face for days, and we've seen tens of thousands of downloads. We are very proud because we've seen the open source community building on top of this, and all of our model weights are also available on Hugging Face as well. You can find our paper, all of our model weights. Our evaluation framework is also open source. It's called Evalchemy. And we have this curator engine for basically scaling inference of your model, which this is also open source available. This QR code takes you to the tweet where there you can find all the links to all our paper and our Hugging Face and our website. So yeah, I want to thank the OpenThoughts community. This was a huge effort. Unfortunately, Ryan wasn't here to present this today, but I also want to thank Ludwig and Alex, our advisors, for their support. And yeah, I'm happy to take any questions.
Thanks. That's a nice work. I just have a quick question. So I saw your slides, the filtering part. You mentioned that the answer filtering does not help, right? I just wonder if you've tried to do some correctness-based filtering.
You mean correctness verification
yeah.
based? Yeah. So we tried verification for code. We tried using the unit tests for verifying samples. For math, we tried parsing the final answers and comparing those against the ground truth. We did not see. You'd like basically we're not showing all different filtering methods here in this slide, but you will see there is like a line down there that's associated to.
Yeah, because in other works, like in open math or open code reasoning, they also mention that for SFT data, actually they find that the incorrect answer could also help. Do you have any intuition on that? So,
like, think about it. Then you're filtering, you're actually shifting the distribution. Like, you could totally be filtering, like, questions that are more difficult because a lot of the times these questions are not correctly answered. So there is, like, I honestly don't know the final answer, but it's like, to me, it's a little bit like helpful to think about, okay, yeah, when I'm actually like filtering out questions that are not correctly answered, this means that I'm shifting the distribution of my questions.
So if your, if your distilled model, like the teacher model, is stronger enough, then does that mean the correctness filtering may help, or yeah, like for difficult problems, if we have some high quality and correct response, maybe that will help. Or
yeah, this can totally, like, honestly, I can't really make a statement because I don't know, but surprisingly, from all these models, what I can tell you is that Quen is the most verbose model. And also note that I think more than 60% of the samples in our data set, our training data set, are not finished. So they don't even have the final answer.
What's your maximum sequence length?
For training is 16K. Yeah.
Okay. Thank you.
Thanks for the talk. I have a question about one point you mentioned about the observation that seems the answers diversity is better than like question diversity in terms of helping the training. So I'm curious because it's kind of counterintuitive, like humans tend to get like more insights from seeing diverse problems instead of like practice the same problem again and again, even though you can see different solutions. So how do you measure this kind of two different types of diversity and how to compare them exactly?
So like the only thing, okay, I don't want to really put it that way that it's basically the question diversity doesn't matter, but we realize that at some point adding lower quality data sets is not helpful. And at the same time, we realize that if you take a smaller subset of questions, but then you sample these multiple times, it could be that you're basically reducing like you're just representing the model with the same question that's been answered multiple times. There's like differences in each answer because of the temperature, but it could be that basically you're just like reducing the noise at the end of the day. Again, these are all like things that I think open questions that need to be like looked into more, but these are just the scope of our observations.
Thank you.
Okay, maybe one more question. Super interesting. If you go back a couple of slides, you had one where I couldn't tell whether,
Yes.
So question quality is helpful, but you had one for difficulty, right? Or something? You had?
So we have question filtering and answer filtering.
Okay, so when you're finding that, so difficulty-based selection, for example, right? Yeah. Is that good, difficulty good or difficulty bad? And same for length selection, is length good or length bad?
Yeah, sorry, I needed to mention this. Yeah, so here we keep questions with basically the samples that have longer answers and samples that have higher difficulty, that are rated as higher difficulty. Yeah.
Thank you.
Perfect. Thank you so much for the talk. Thank you.
Thank you.